Okay, now we are going to linear algebra and some topic which was not always done in the linear algebra courses in the earlier years. I think nowadays it's a standard topic. It's the so-called singular value decomposition and the pseudo-inverse. So the PINV command was actually something I learned when I started MATLAB in '89. And I was wondering what it is, and it's a strange modification, generalization of the inverse command for square matrices which are non-degenerate. But PINV can be done for any matrix, so I think it's nice to understand it, and also the relationship to the minimal norm least square solution. That's a topic that you're doing quite often. So I think only the left part of the screen is relevant for you, and I hope that I can go through the script relatively quickly, trying to explain to you why I was doing this, and at some point I may do some changes. So the first thing was I want to demonstrate the role of the PINV, and actually for those who are taking a frame course, we will come to the notion of a dual frame via the PINV, but that's not the topic at the moment. So I want to have a general matrix of rectangular format. So how can I generate a random matrix of format 5 times 4, which has rank 3? So it should not even have maximal rank. And the easiest way to do it is to multiply two random matrices of corresponding format, but so to say they're mapping. The first one which is applied is mapping from R4 to R3, the second from R3 to R5. So overall the composition is mapping from R4 to R5, but since it goes through a three-dimensional space, clearly it will have rank at most 3, and because it's random, it's with high probability, probability 1, it will be rank 3. The second thing, I wanted to have a square matrix, which should be positive definite for some reason, because it's the most interesting part. So I take a random matrix. Here I do what I do very often. Instead of avoiding, sometimes if you would test with random matrices with the random, you would only test for positive matrices with entries between 0 and 1, uniformly distributed. So I want to have negative values. I could do complex matrices or so. And then I multiply the matrix, which is transpose conjugate. So in this way, I clearly get a positive definite symmetric matrix. And because, again, it's random, it's not surprising that the rank of this matrix, rank of A is 3, and the rank of this positive definite matrix is 4. So because it's full rank and it's positive, it's strictly positive definite. Now, the command SVD is realizing the singular value decomposition. And the short way of explaining why the singular value decomposition is relevant is based on the observation that it's, of course, very nice to have a diagonal representation of a matrix, because then it's easy to get the inverse or to take the square root or even the square root of the inverse and so on. Well, you do it for diagonal matrices, and then you do it pointwise for the entries in the diagonal. So the question is, which one of the matrices are diagonalizable? Now in MATLAB, we could do the experiment that, yeah, maybe I add something here to enter a new section, and I'm making another matrix C. Wrong keyboard. C is random, and this is my command. This is no specific, maybe just 5. A random matrix with complex entries between, symmetric around 0, both real and imaginary part. And the eigenvalue routine is saying I'm getting a collection of eigenvectors and a diagonal matrix. I call it DC. No, it's autocomplete is not good. And this is supposed to be the eigenvalue of the matrix C. And then, of course, the question is it true that I want to verify that this is really a collection of eigenvectors. Now, what does it mean to have eigenvectors? Eigenvectors are vectors which applying the matrix now by matrix multiplication to the collection of columns. So this is a system of eigenvectors. Matrix multiplication applies to the first column, second column, third column. And this should be the same as taking these vectors and multiplying them column-wise with the diagonal entries in the diagonal, and multiplying with the diagonal matrix from the right should give 0. So should give the same thing. So yes, it's true. And of course, we can modify it and say, well, is it true? Here, actually, the operator norm is determined that you have the inverse of VC with C with B is minus the original matrix C, taken in the Frobenius norm, so as if it was a pixel image, and rerunning it again, we should also have 0. Oops, inverse of V of VC. So here is the typo. What's wrong? C. No, I think sorry, that's completely wrong. It should be so I multiply C times VC with inverse from the right. So C should be the same as, I shouldn't do so much improvisation, should be VC with DC with the inverse of VC. So let's try it again. Yeah, this is okay now. So yes, surprisingly, almost every matrix is diagonalizable. And in the courses, you only hear that you need symmetry or at least normality to have diagonalizability. And the trick is here you are allowed to take a general basis. So somehow, why is this a plausible thing? Because a random matrix has a more or less random characteristic polynomial. A random polynomial will have separated zeros, so no multiple zeros. If for every zero of the characteristic polynomial you get a vector, this is a system of linear independent vectors, so it's an invertible base matrix if you put all these vectors into a column vector. And so diagonalizability is fine, but the question usually, it's more interesting, do I really have to do the inverse matrix? Can I use the transpose conjugate? And then you need orthogonality of the vector system. And that's exactly okay if the matrix is normal. So if and only if the matrix commutes with its transpose conjugate. So it means that if the matrix is C, if C multiplied with C prime is the same as C prime with C. So whether you multiply it from the left or from the right, it's the same. And of course, for random matrix, this is very rarely the case. So only a set of measure 0, so to say, is orthogonally diagonalizable, but this is the case, would have been the case, for example, for our B. We'll come back to this later. So what is the alternative if you have even a rectangular matrix? You're trying to choose a basis on one side of the domain of the operator, and on the other side, you're putting all these orthonormal vectors into a collection of the square matrix. So to say that U as V is the singular value decomposition has to be read as there is a basis on one side of the domain. And if you look at this here, the next step is the order in which they appear is exactly the one that you need to write A. So A is of the form U times S times V prime. Now, V prime is transpose conjugate, is of course unitary if and only if the matrix is unitary. So why don't we just say V prime is output so that we can write this product? And the answer is, well, it's much better to say, well, a matrix representation means that you're choosing a basis on one side and then a basis on the other side. Now, the description of the operator comes in the way that you're saying, well, give me the coordinates of your vector in the domain. and that's done by the V prime multiplication. So applying the matrix to vector A and factorizing the matrix really means given the vector A, so here it's the matrix is format 5 by 4, so it's mapping R4 to R5. So given a column vector of size 4, so you apply V prime. So V is an orthonormal basis in R4. U describes an orthonormal basis in the target space. So according to what I call the domino principle, the S has to be a rectangular matrix of the same format as the matrix A. And this description as matrix factorization just says, well, take coordinates in the V system, rescale them, and this matrix S will come here. No, will come later. Maybe I should display them. Display it even if it's already here. So I hope that I'm not destroying the data. So the matrix S is a rectangular matrix, but it's supposed to be a diagonal matrix. So it's clear that this cannot be a perfect diagonal matrix. But what you see here is the diagonal entries are non-zero at positions 1, 2, 3, or 1, 1, 2, 2, 3, 3. So actually the diagonal, which is the diagonal up to the 0 here, is the scaling factors. So the operator can be described. Take an orthonormal basis in the V system, then scale it with the factors which are in the diagonal, and then you synthesize it, which means in the range clearly 2 vectors are not appearing. U5 because it's not even possible, I don't have a 5th column, and U4 are not. So you can say, well, the range of the column space is clearly the same as the linear combination of the orthonormal basis of U. So we have full information about the column space or target space of the operator A. It's 3-dimensional, but we even have an orthonormal basis for this, and it's the first 3 columns of the matrix U. So that's maybe interesting. Now, another way of direct verification is that the connection between the vectors V and U is with my comp norm command. I'm just saying, well, let's compare the action of matrix A on the first column vector of my orthonormal system and compare it with the vector U, and you see it's a scaled version. And if you rescale it to have it length 1, you will get they're numerically exactly equal. And this factor is exactly the first entry in the scaling matrix. Of course, the same, if you look here, the second value here is exactly the same, and you can do the third and so on. So we have now full information. So an intermediate thing, maybe not very coherent, is now if I look at the same thing for this positive definite square matrix, I didn't put a semicolon, but that means that these values are displayed. So you really see it's the vector, the V is the basis of an orthonormal basis of vectors in R4. The diagonal entries are these. And then, of course, you can look at the condition number of this matrix. It's an invertible matrix. And the condition number is either the norm of the operator multiplied with the norm of the inverse operator. But of course, the norm of the operator is the maximum of the diagonal entries, which is this well. And the norm of the inverse operator is the inverse of the minimum. So you just take the quotient of the 2 biggest and smallest eigenvalues. So a good matrix is supposed to be one where this factor is small. So in this random experiment, this example, the condition number was not so nice. I think most of the time it will be better. And here you see it's just for numerical verification of this thing. Condition number will be used blindly. We want to see that when is a Gabor system a good Gabor system? Of course, at those points where, at these cases where the condition number is good, but it's also the quotient between minimal and maximal eigenvalue. Now, another story connecting the abstract theory with the concrete story, we could, of course, do the singular value decomposition of a matrix. And you may think that this is always the same as the eigenvalue if you are allowed to do this, but it's not necessarily the same. A good example would be, let's say, a reflection operator. You would like to describe, maybe I should do it separately. Yeah, maybe I start another experiment, another little line. But first I want to explain this. So here I'm saying the Gram matrix, yeah, okay, maybe I should let me see, yeah, maybe I leave out the discussion or so. Essentially, what this was prepared to tell you something about the role of the inverse of the square root of the Gramian matrix. So maybe we just discuss, or I explain very shortly the second line of this. So the Gram matrix is, of course, the matrix where you have all the scalar products of all the columns. So again, MATLAB spirit, matrix is a collection of column vectors. Given two column vectors, the scalar product of x with y, it should be conjugate linear in the y component, in the second component in mathematics, not in physics, has to be y prime with x. That's why here you have all these scalar products of all the columns with all the columns again. So if this is the unit matrix, we are happy because then we have a unitary matrix or so. And the idea is that we can do such a command, take the square root as a matrix. So when can you do this? Definitely when you have a positive definite matrix. So in the background, I'm not sure, I think it's doing diagonalization and doing this. And we can even take the inverse of the square root. We could test that the inverse of the square root is the same as the square root in the matrix sense of the inverse, or is the same as the diagonal matrix. If you have a diagonal matrix as taking the entries diagonal, I mean, point-wise, coordinate-wise, and so on. And so the interesting thing, maybe I should change this to say, well, if you're giving me this command, probably I was should say demonstrate that this is now an orthonormal system. So this is actually my command. I think I was going in the wrong direction. This is a 4x4 matrix, so it's supposed to be a unit matrix. Let me see. Yeah, okay. So this is a more reasonable explanation of what I want to show you here. You all know Gram-Schmidt. Gram-Schmidt is a very nice method to obtain from a basis in a vector space, even a subspace, an orthonormal basis. But we have shown last time already, if you take shifted functions, then it is not a good idea. You should do this symmetric. And the symmetric way is the method can be described as compute the Gram matrix and then take the inverse of the square root. So maybe we also make a test to demonstrate what I was showing, square root matrix of GRB and minus the square root of the matrix of the inverse of the GRB. I hope that's working now. Yeah, so you see it's numerically, because we have not a well-conditioned matrix, it's not so nice, it's not almost perfect, but it's still reasonable. So it is, of course, theoretically it should be perfect, but in an ill-conditioned case, and but for both cases, we are getting something which is almost an orthonormal system, and these two things are almost the same. Okay, now I'm coming back to the connection between the singular value decomposition. I had a technical problem in my preparation. That's why I had to rerun the USV. So remember, we have this. Just to verify that U is really an orthonormal basis, let's compare the Gram matrix for the system U. I determine all the possible scalar products of the columns of U. And this is a 5 by 5 matrix because it's the target space of our operator A with a unit matrix. And it turns out, yes, this is the identity. The same for the orthonormal system described in the V space. That's the domain of the matrix A, and everything is fine. Now, what I want to show you also is that you have a lot of concrete things in your hand now. So if you are interested in a singular value decomposition or refresh your knowledge, I recommend to look at the book of Gilbert Strunk on linear algebra. We have copies at NUAC, and I can bring it maybe next time in the course. And here he's always explaining that every matrix has 4 spaces. Now, if I would be in class, I will try to do it in a very simplified way on my screen now. It's you have a domain and a target space. And now at the side where I have my, let's say, white pencil or so, I would say the mapping usually is going from one space, this one, to the other space. And we're saying, okay, we understand that the columns are generating the targets, but the range of the mapping. So these are the columns. And this is the null space, which is, of course, part of the orthogonal system. But with every matrix A, I also have a matrix A prime. And the matrix A prime has a null space and has a target space. So we usually call it the row space of a matrix, but you cannot apply a matrix to a row vector. Therefore, you should think of rather the columns of the transpose matrix. So to make it short, for every matrix, we actually have 2 systems of vectors, the columns of A and the columns of A prime. Each of them spans a certain space. We call it the column space, and by misuse of language, we call it the row space of A. It should be the column space of A prime. And we have corresponding null spaces. And what I show you by this picture is, it turns out that they are perpendicular. So the pseudo-inverse is actually saying, well, if you give me in the target space a vector which is not in the column space, we can modify this operator and we project it into the column space. And once you have it in the column space, there's a 1-to-1 correspondence between the row space and the column space. So applying the matrix to the row space gives you the column space, and that's a 1-to-1 mapping. So the corresponding mapping here is this one here. I mean, I'm doing this now very quickly because it's difficult on the screen. Now, assume somebody would have another generalization. It would differ by something from the null space. So all these elements along this specific solution, which is the pseudo-inverse plus the null space, would give as the same target space. But looking at it properly, you would say, well, they are all longer. So the minimal norm solution is really the element in the row space, which is uniquely determined to the projection on the column space. So this is very quickly and much too fast. I have written documentation, but this is why we might be interested in these 4 spaces. And in order to be interested in the 4 spaces, also in more abstract situations, we have to understand the projection operator. And as I told you, the range is 3-dimensional. U is an orthonormal basis. And using the first 3, we can get the orthogonal projection in this way. So it's, instead of writing, you take the first, the second, the third coordinate, it's an elegant way of writing the projection operator by saying, apply this matrix to a column vector in R5. You get 3 coordinates, and then you're doing synthesis with these column vectors. So you're exactly describing the 3 coordinates in the U system. And we have understood, think of this picture, that this is the range space. And the corresponding 2-dimensional space is the null space of A prime. I don't go too deep in this because it's a little bit confusing, maybe so abstract, but I think you should repeat it from time to time. So first thing is it a symmetric matrix? Yes, obviously, I don't have to check it. Is it an idempotent? Is it the projection operator? And the answer is, well, I just try it out. And yes, it's idempotent. This is numerically equals 0. Also, this is a late checking of all the dimensions. So the matrix S at the end has the same format as the original matrix A, and so on. So now, what I'm knowing at this point is I expect that this is an orthonormal system for its three-dimensional subspace. And this is an idempotent which is self-adjoint. So by abstract arguments, we can say it must be the orthogonal projection on some three-dimensional space. But now I'm testing it, and I'm testing it whether it leaves the column space or the range space invariant. Now, what is the best way of checking that an operator leaves a space invariant? You take any generating system, and of course the naive generating system for the column space of the matrix A is all the columns of the matrix A. So if the matrix, which is supposed to be the projection operator on the column space applied to the collection of columns of A, is giving the same as the original columns, then we are sure that this operator leaves all the columns and therefore the column space invariant. On the other hand, the singular value decomposition tells us that this space is three-dimensional and the U1, U2, U3 are a basis, an orthonormal basis. So this is one way to describe the orthogonal projection operators. The other way to gain it, that's maybe a bit risky, but I will still try it, would be to say we combine the operator with the pseudo-inverse. So your p call minus. Now you're saying, well, I think I would like to get the projection onto the column space. So I'm trying it now with my demonstration, but it's very difficult. You're saying, I want to project this point, this point to the column space. So what you can do is that you're saying, well, first I apply the pseudo-inverse, which is projecting onto the column space, and then going back to the time domain, and then I apply the matrix. So if you first apply the PINV, then the matrix product will look like matrix A with whatever this called pseudo-inverse is, sorry. Not sure what's going on. Yeah, here. PINV of A, this is supposed to be the same, and yeah, maybe I just do the ordinary operator norm and run this experiment. And you see, this is the same. Now, you can discuss which method is the more reliable one. You could also take the columns. You could apply Gram-Schmidt. These are all different methods to define the projection operator. Now, the same thing, and I don't think you have to check it, is to verify that the projection operator on the row vectors is the same, where I'm just taking, well, we remember rows are columns of A prime. We just take the basis, the orthonormal basis in the four-dimensional space where our matrix A is starting from first to the last in the sense of a rank. So R is the rank, which is 3 in our case. And then you verify that now this, and that's maybe the interesting point. Maybe I add this in the comment for your documentation. Recall rows are columns of A transpose. I'm writing in this way because I cannot write a comma here in this text string or so. Now, the next thing, that's the question. Once we have understood basically that every matrix can be written in a diagonal form with unitary or orthonormal basis on both ends, so done properly, there's one more thing that I should mention is that this is not exactly the same as eigenvalues even if you're doing eigenvalue decomposition, because the singular values are always positive. And why? I mean, there are good reasons for this. So if your matrix might be, was starting to explain this, a reflection matrix. So if it would be reflection along the XY plane. Maybe I'm just doing it spontaneously. Where is my win? Yeah, oh, sorry, do a new section. Yeah, so if I say reflection is I of 3, very simple, but a reflection of position 9, just to make a joke, you could write 3, 3 is -1. Then, of course, running it would, of course, show you this is simply the reflection operator. X unit vector in X and Y direction are left invariant. The unit vector E3 is going to minus E3. And now, if you would do VR, SR, UR. Usually, standard notation is USV, is SVT of ref. I'm not so much interested in the others, but I would like to show you that you're getting. Yeah, maybe I'm looking at UR. So we have this matrix. We're getting the S matrix, which has the same values, but the absolute values of the diagonal. And it's telling you, well, it moves the standard matrix, but then in the orthonormal basis, in the basis space, it's with a -1. So instead of putting the -1 into the diagonal part, it tries to just take another orthonormal basis in the range space. So this is very typical for the singular value decomposition, and more or less for diagonalizable, orthogonally diagonalizable matrices, the only change that you have. Now, going back to this, one can explain the pseudo-inverse or the computation of the pseudo-inverse through the singular value decomposition. So roughly speaking, again, I'm using my geometric model. You're saying, well, you have a mapping, and the mapping is actually composed by projecting onto row space, then moving over from the row space to the column space. And actually, somehow, every matrix is just an isomorphism of a three-dimensional subspace of R4 into a three-dimensional subspace, I mean rank 3 matrices, into a three-dimensional subspace here. And we're even able to choose an orthonormal basis and describe it with non-negative diagonal entries. This is what you can do. So what is the best inverse that you can do? Well, you invert the part which is invertible, and the rest is just left 0. So you're saying, well, the general situation to the forward matrix is projecting to the row space, then moving over in a bijective way to the column space, and then you're done. You could say and embed it into R3. And now the opposite is project on the column space, invert the invertible part, and you're inside of the row space, and you can still view it as a mapping into R4 in our case. So the simple, looks like a self-circular explanation is that you would say, well, you get the pseudo-inverse of A by inverting each of the matrices. You change the order, and the inverse of the S matrix is this one here. Now the trick is this is again a diagonal matrix now, of course, of the corresponding transpose format, and the diagonal entries of the original matrix were this. And if you just take the pointwise inverse, so this is a vector, you see roughly 4, this is roughly 1/4, and so on. So this is pointwise. But, and that's the interesting part, of course, here, and that's why I took an example of rank 3. If you have a 0, then you cannot invert it and you leave it 0. Now, in practice, there might be a value 10 to the -5 or 12. And depending on the application and the precision of your data, you might say, well, it's so small, it's probably just a numerical error and should be a 0 and should be ignored, or I have such a precise matrix description that I would like to keep this information or so. So that's then the value PINV with the threshold. That is just a value that would allow to invert not only values which are 0 in the strict sense, but which are kind of too small to be realized. I mean, you can also say it's we are dealing with a minimal norm approximation, and we are not willing to pay an arbitrary high price. So the lengths of the coefficient vector which are delivered should be somehow limited by this threshold, and of course the length of the vector that you would like to represent. Okay, so just to convince you, if I'm saying that this is true, then if the answer is 0 and it's virtually, then it's more or less an indication that it's not just another way of looking at it, but this is how it is done. So that's really how MATLAB is, as far as I know, computing it. It does singular value decomposition and then does the pseudo-inverse of S, but not by this command, but by taking the diagonal values which are non-zero, inverting them. And if you're having a threshold, so PINV S and I don't know, 1000 epsilon, 1000, the precision of your matrix, then you would get the same thing. Now maybe since we are having no kind of real value, here I could put 0.1 and the matrix is, and it would say, well, my smallest non-zero entry was larger than 0.1, therefore it's exactly the same result. And you can change it, and if you would put, maybe just we put 0.3 here, just to show you the effect, then you would see that's surprising now. Did I do the command? Yeah. Okay, so that's for me not clear. I'll put in 0.8 here. Okay, I have to check why is this true. So probably I should erase it in the documentation, but this is not what I meant to explain to you. Okay, so once more, pseudo-inverse is just inverting the process. So you can also say it in this way. The pseudo-inverse matrix has an action which says, take in the target space all the coefficients in the U coordinates. Now we have seen only 3 of the coordinates are non-zero, so actually you don't care about U4 and U5. You multiply with the inverse of the non-zero scaling factors and you're synthesizing. So again, you need only the components V1 to V3. And therefore, of course, the range of this is again the row space of the original matrix and so on. Now, yeah, here you can see again that I was doing this more or less by hand. I was putting the inverse with the 1/over command. 1/over is a private command, but it just says if you have a vector which has potentially 0 components, you can pointwise doing a division, and wherever you have a 0, you leave the 0, and you have 1/over also with threshold. Okay, now I wanted to tell you another little thing which came to my mind, which is very easy to present in MATLAB, and that's, is it true that the pseudo-inverse of a product is the same as the product of the pseudo-inverse matrices? And of course, you can take random matrices. I took 2 random matrices of size 4, and then this result shows, oh yes, it's the same. But then, of course, I have to tell you, this is a bit of cheating, because if you're doing the pseudo-inverse, maybe I even compute here the norm of inverse of M1 minus the pseudo-inverse. So the trick is whenever the inverse exists, it will be the same as the pseudo-inverse. So you could say the pseudo-inverse only makes sense if there is no inverse matrix. But this is again not true in the practical sense. If you have a very badly conditioned matrix, so a bad and nasty matrix, and you're computing both of them, they might look different or be different, numerically different, not the same. Then I would say, well, please use the pseudo-inverse. In most of the cases, it's much more reliable, but it's also more costly. So if you think of large matrices, the speed of doing the singular value decomposition is slower. I mean, you need more time to get SVD and therefore PINV compared to the very optimized inverse. So think of inverse for good situations, perfect, better, cheaper, and for bad situations, maybe not reliable, but fast, and the other one is more reliable, more robust. Okay, so you see here, the result tells you it's not, MATLAB is not saying, well, I compute the determinant, and because it's non-zero, I take the command inverse because I know the inverse is the pseudo-inverse. No, it's really computing two different matrices, but a random matrix might, in most cases, small random matrices are not so bad. So in this case, this is okay. So actually what we are testing here is the product of invertible matrices is invertible. So yes, of course, we know the rules for inverse matrices. So I thought, well, in order to demonstrate it, I take some rectangular matrices and I was choosing this, and I was I didn't reflect much, and you can try the same. And it seems that in this situation, I mean, all my few experiments were fine. It's indicating in such a situation, they still commute. And then I said, well, maybe I have to change the dimension, make the second dimension of the matrix larger, and hold it below it. It really is different or so. So this last experiment, line 55, demonstrates that it's simply not true that the product of pseudo-inverse matrices is okay. And there are criteria for this. For us, this is not relevant, but it's a warning. So it's saying that in the case of the singular value decomposition, there's a specific configuration, and it's okay to say we know what the pseudo-inverse of a rectangular diagonal matrix is. That can be described directly by the definition. And in this case, we can use this formula, but it's not a general rule to determine it from the product. Now, at the end of this session, which turned out to be a little bit longer than expected, I would like to show you my favorite formula for the pseudo-inverse. And it's really very useful and not so extremely well known. Also, implicitly, it's used in many, many places. So when I started to use the pseudo-inverse, I even wrote a small paper on this because I observed that most people were using something similar without noticing it as a general phenomenon or so. And the idea is whenever, here the last is the inverse is the pseudo-inverse, but these two, line 59 and 60, are relevant now. So my memorizing way is, if you're interested in the matrix A, then what you have to do is you write A prime, A prime. And then you decide whether you take the second part and write it here. And then, of course, the A prime is left to the left. Or you're combining the two sides on this here. Then you have the pseudo-inverse of this here, and you have this. Now, actually, I might add something more. Because in the case of dual frames, we would say that we take the first formula, but we were computing, maybe two things. We can compute the pseudo-inverse of A prime, or we take the pseudo-inverse and then we take the transpose conjugate. So that's one thing that we should know, that it's the same. Or when we are coming and you're giving me a collection of matrices, which are a frame, well, it just in linear algebra, you would say it's a generating system. So your vectors, you have more vectors than needed, but they span your column space, so the target space. Then, of course, I have to take the prime of this formula and change the order. So I'm taking the first formula. I'm saying, what is the prime of this here? And of course, the A prime is getting the A double prime, so it's coming at the end. And in the front, I have to take the pseudo-inverse. of A with A prime. I put it in a prime with the A. So I'm doing a comp norm now here. And yes, this is a way to do it. So for those who are already familiar with frame theory, I would say, well, my general way of getting a dual frame in a linear algebra situation is write those vectors into the matrix and take the pseudo-inverse, and then you take the transpose conjugate, or you're writing the column vectors and you apply the pseudo-inverse of this matrix here. Now, the interesting thing is here, the matrix A with A prime is already symmetric. So that's why I leave it here, but of course, it's not necessary to take that one prime, but I think natural would be to have the prime, but now we leave it out. And I would say, if you're happy with this, then you take always the pseudo-inverse or so. Now, if this is a matrix, and that's not true in our case, our matrix is rank 3, it's not spanning R5 or the target space or so. But if this matrix A would be invertible, you could always take the inverse or so. So also going back to the original one, so the question is, when would you use this matrix? Maybe just recall, what is the size of A with A prime? And I would say that's the frame operator for those coming later. Frame operator like matrix. And the other one would be the size of A prime with A, which is the more or less the Gram matrix. Okay, I'm rerunning it. So the first thing is, of course, I have nothing changed actually. It's the same error. No. Oh, it's funny. Yeah, it's so kind of, you see, it's numerically computed, therefore it's not exactly the same. On the paper, it would be exactly the same by the symmetry or so, but numerically it's not the same. And of course, what you can see here at the very end, is that think of a system which is, let's say, highly rectangular. So think of a generating system with 500 vectors in a 20-dimensional space. And one of these matrices would be 500 by 500, and diagonal, determining a basis and so would be singular value decomposition would be very costly, but determining the smaller dimension, everything is fine. So essentially, we will see this in the setting of frames, Gabor families which generate frames. We will always use this frame operator, or when you're talking about linear independent systems. So these are maximal matrices of maximal rank, which are high and thin. So if somebody is giving you 7 vectors in R12, you would say, oh, hopefully these poor 7 vectors in this big space of 12 dimensions, at least they are linear independent. And so this is really bringing you to the notion of array spaces. And as the word explanation already says, in the earlier phase, we are close to the discussion of frames. So I think I have done the material which I have prepared for now for this part, and I stop the recording and we will continue with Gabor stuff.